Oops, go ahead. Okay, so I want to do a couple of the problems off of the worksheet from yesterday just to make sure people are doing okay with it. So I'm going to start off with problem number 2. Number 2 here, we have a 28-foot span, and we're given a 14-foot setback, 10-12 slope on the main roof, on the common roof. What does that 14-foot setback tell us? Since it is half of the span, half of the 28-foot span, it tells us that these slopes are the same. So this is also a 10-12 slope here. So this is a conventional case. Step 1 is still to find, if I spell correctly, the height of the common. And of course, we're referring to the common rafter there.
I have a question real quick.
Yes, sir.
All right, so how do you have two different angles there? I mean, how do you have the same angles but a different distance?
For which one? For what do you mean different angle or same angle?
All right, all right, so you got the 10-foot slope on both sides, right?
Oh, yeah.
Or I suppose if it's a 14-foot from the bridge to the end of the road.
Yeah, it's not drawn real well. My angles may look similar or not similar, but they should be. This angle here and this angle here should be the same.
Oh no, I'm not even looking at that. I'm just looking at the numbers, and I'm brain farting. Don't worry about it.
Oh yeah, yeah. The 1412 being half of the 28 means that this is a square here. So then for the height of our common, we got 10 over 12 is our slope. That's going to be based on a run of 14 feet. That goes on bottom. H is our height. Cross multiply and divide, we've got 10 times 14 divided by 12. Gives 11.667. Feet is our height. And now we need to find, for step 2, the length of our common. Which, of course, is the square root of that 11.667 squared plus the 14 squared. $18.224. Feet. That is the length of our common rafter. So that means if we come over here, this is 18.224 feet. Now step 3 really doesn't have anything to do on this one since it's conventional. The slopes are the same both ways. Length of the longest jack is just the length of the common. So this is 18.224. And we know that the peak is in the middle. The distance from the corner of the house to that longest jack is 14 feet. Now we're going to use that to find the next longest jack. So we have that 18.224 and the 14 foot on that triangle. Our next longest jack's going to be here, again, assuming 2-foot spacing. Call that X. It's going to be 12 feet. So we set up a proportion. 14 goes to 12 as 18.224 goes to x. Once again, we cross, multiply, and divide. 12 times 18.224 divided by 14. Giving us 15.621. That's the length of that next longest jack. And of course, our last step is to find the decrease. So the decrease is simply subtraction. 18.224 minus 15.621. 2.603 feet is that decrease. And we'll write that out in feet, inches, and sixteenths. So we got 2 feet. 0.603 gets multiplied by 12 to make it inches. So that's 7 inches. We subtract the 7. And we're going to turn our 0.236 into sixteenths. So times 16 is 3.7, which is 4 sixteenths, which is a quarter inch. So the decrease there is 2 foot 7 and 1/4 inch. Now, because this is the conventional roof, that'll be the exact same decrease on this side. Remember, 2 things about a conventional hip. Because the slopes are the same, the rafters will actually meet on that corner rafter, that hip corner. So they will actually be in the same spot, come to the same spot. Second is the decrease from one rafter to the next will be the same in both directions. This decrease here will be the same as that decrease there. Any questions on that one? Then I also want to throw up there one like number 5. I feel like number 4 and number 5 are very similar problems because they have different slopes. So it's an unconventional hip. The conventional hip up here, we could have actually just looked at our framing square, looked under the decrease in jack rafter for 2 foot on center or 24 inch on center, gone under the 10, and we could have found 2.603 would actually be listed on the framing square for us for that decrease. We would still have to be able to convert it into feet, inches, and sixteenths. Actually, it'd probably listed as 30.03, probably listed as all inches on the framing square. But still, we need to be able to do that conversion. So anyway, let's take a look at number 5. I think it's more difficult to do the unconventional hips when we're given both slopes than it is if we're given the main roof slope and the setback. Mainly because if we don't have the setback, we're going to have to do a calculation to find the setback. So we have a 40-foot span here, 412 slope on the main roof, and an 812 slope on the hip end roof. So we're still going to find the height and the length of the common rafter. I'm just going to label that common here, and I'm going to combine a couple of steps rather than writing out the whole step. So this is 412 because the common rafter is over here. This is a 412 slope, and this is a 40-foot span. This is where our height is. This is our run of 20 feet. We're going to have 4 over 12 equals h over 20. And we'll cross, multiply, and divide. 4 times 20 divided by 12. I believe that gives us 6.666. Does. 6.667, we're going to call that. Now we need to find the length of our rafter. That'll be the square root of that 6.667 squared plus the 20 squared. It's 21.082 feet. So that is the length of that common rafter. So that's right here. We're going to need that later, but for right now, we're going to now look at the longest jack. And I'm going to say hip jack because it is on the hip side. So what we're looking at on our main diagram is actually this rafter right here. And we're looking at from the side. So we're going to be looking at from this side. You know, the height of that is the same as the height of our common, 6.667 feet. And we know the slope is an 812 slope. So this down here is our setback. That's this dimension right here. We're going to find it using our slope. 8 over 12 is 6.667 over that setback. When we cross multiply and divide, we get the setback 10 feet. Next, from that longest hip, we've got the setback. We also need to find the length of that longest jack. That's simply going to be the square root of 6.667 squared plus 10 squared. Giving us 12.019 feet. So up here, this longest jack, 12.019 feet long. Now, because these are different slopes, there's a different decrease on each side. So we know this distance here is half of our span of 20 feet. Our next rafter is going to be here at 18 feet. And we'll call that length X. So let's look at that one first. We've got 20 feet, 12.019 feet. We're comparing that to 18 feet and X feet. 20 to 18 is the same as 12.019 to X. Cross multiply and divide. 18 times 12.019 divided by 20 gives us 10.817 feet is that next jack. So this is 10.817 here. Now we'll subtract to get that decrease. 12.019 minus 10.817. Be at 1.202 feet, which is 1 foot. 0.202 times 12 is 0.2424, or 2.424. So 2 inches. Subtract the 2 and then times 16 to make it sixteenths. 6.7 is 7/16. That is the decrease on the hip side. We're going in this direction. Each of these jacks is going to be 1 foot, 2 7/16 inches shorter. Now we need to find the decrease on the main roof side. We've got the longest rafter there, the 21.082, and the setback of 10 feet. The next one is going to be here at 8 feet, and I'll call that length Y. We're at 21.082 and 10. The next one, this is Y and 8. So our proportion here, 10 is related to 8. in the same way as 21.082 is to y. If we cross multiply and divide here, 8 times 21.082 divided by 10. Giving us 16.866. So the decrease there, 1.082 minus 16.866. $4.216 feet. So it'll be 4 feet. Take the 0.216 times 12 to make it inches. That's 2.5, so that's 2 inches. Take off the 2 whole inches. We got the 0.592 times 16. That's 9.4, so that's just 9/16. That is the decrease on the common roof side. You'll notice when we have a conventional case up here where the slopes are the same on both sides, the decrease is somewhere in that 2 to 3 foot range. And it's, like we said, it's the same on both sides. When it's an uncommon case where we have different slopes on each side, one of the decreases will be much smaller, usually smaller than 2 feet, and the other one will be much larger. And that's because of that difference in slope. It has to make up for that difference in slope. Anybody have any questions there? You all feel great about doing these, repeating them on a quiz someday, like Thursday or so? Okay. So let's go ahead and get to our next step here. Our next step is to talk about valleys. The math in calculating valley jacks, and more specifically the decrease in valley jacks, is exactly the same as the math for doing hip jacks and the decrease in hip jacks. In fact, if the slopes are the same, the decreases are the same. It's just the picture and the geometry that you draw out is a little bit different. So what we're looking at here is what is called an L-style roof. So we have a main roof, and we have a small piece sticking out of that main house. So this is the main roof. This down here is called the L roof. That's just spelled E-L-L. So the L, of course, forces us to form a valley. And when we frame that valley, you got a common rafter here, but the next rafter, of course, is going to be shorter, and the next one shorter. Those shorter ones are called jacks, just like they are with the hips. Well, we also have a common rafter there, and the next one gets a little shorter and a little shorter. Those are also jacks. If the two roofs are the same slope, if the L roof and the main roof are the same slope, the decrease from here to here will be the same as the decrease from here to here. It will be the same decrease on both sides of the valley. Notice now on the hip roof, the bottom of the rafter stayed in the same spot, and it was the top end that was really being cut back. Here, the top end is staying in the same spot. It's the bottom that's being cut back. But again, it's the same cut, same angles, same amount to form the valley. So let's look at an example here. And in this example, I want to make it as simple as possible. Let's make this a 28-foot main roof with a 28-foot L. And we'll call this a 612 slope over here. Now you might be wondering, well, what's the slope of the L? Well, the picture tells us the slope of the L. The reason being, the peaks match. Because the peaks match, and they have the same slope. Both of those must be true, but because both of them are true, then this is also a 612 slope here. The slopes of the two roofs are the same. So if we have the same span on both roofs and the peaks match, they must have the same slope. So we're going to start out with the same step. We're going to look at the common rafter. We're going to look at the height of the common first. And here it really doesn't matter what direction we take the common rafter. Typically, however, the common rafter is on the main roof. So we'll go on the main roof here. 28 feet, looking for the height, and this is a 612 slope. We've got a run here of 14 feet. Our 612 slope, 6 over 12 equals h over 14. When we cross multiply and divide, 6 times 14 divided by 12, we get a height here of 7 feet. Our second step, once we found that height of the common, once again is to find the length of the common. So that length there is going to be the square root of 14 squared plus 7 squared. Equals 15.652. So this distance is 15.652 feet. Now, we are ready. That common rafter is our longest jack. We don't even have to rewrite it because it's in the position of the longest jack. So we jump to that next step, which is the next longest jack. And this distance here, since the peaks match, it's just going to be half of this span, 14 feet. And we'll be looking for this jack here, which I'm going to call X. That, of course, will be on 12 feet because it's 2-foot spacing again. We've got 14 feet, 15.652. We're comparing that here to X compared to 12. So again, we have our proportion. 14 relates to 12 the same way as 15.652 relates to X. And we can cross multiply and divide. So 15.652 times 12 divided by 14. We get 13.416. That is our next longest jack. So our final step is to find that decrease. 16.652 minus 13.416 gives us a decrease 2.236 feet. Now that should look familiar. That's the same decrease we had on a conventional hip end when both slopes were 612. 2 feet, take the 0.236 times 12, get 2 inches. Take off the 2 whole inches, we take the 0.832 times 16, gives us 13.3, so it's just 13/16. 2 feet, 2 and 13/16 inches. Any questions there? So now this becomes a little bit trickier if our spans are not the same. Typically the L coming out of the side of the house is not the same span as the main roof. So let's say we have a 44-foot span on the main roof and a simple 20-foot span on the L. If I tell you that this slope is 812, I tell you that this slope here is also an 812 slope. This is again a conventional case. You'll notice here the peaks no longer match. This ridge no longer comes into the main ridge because it can't. On the same slope and a smaller span, it's going to be shorter. It's not going to be near as high. So that peak cannot come in. So that's the part we have to account for here. We're still going to start with the common rafter. "44 feet and an 812 slope. This is my height. And of course, this is a 22-foot run. 8 over 12 equals h over 22. And we cross, multiply, and divide. 8 times 22 divided by 12. 14.667. Now we still need to find the length of that common, and that'll be the square root of that 14.667 squared plus the run of 22 squared. Giving us the length of the common is 26.441. So that again is this right here, that length of 26.441. Now we are then looking at the jacks. The 26.441 is the longest jack, so we're looking for the next jack, which would be right here, 2 feet over. The problem is since the peaks don't match, we don't have that triangle built in, so we've got to force it. If I extend this up here, this distance, since they are the same slope, that distance is just going to be half of this span, the 22 feet. Now we're going to look at an example a little bit where it's not half of that span, but that'll be with different slopes. So that's 22 there, and of course this would be 20 here for that length. We'll call it x. So 26.441, and this is 22. Next one, x and 20. So the 22 goes with the 20. And of course the 26.441 goes with the x. We cross multiply and divide to find x. 20 times 26.441 divided by 22. 24.037. And we subtract to get the decrease. 26.441 minus 24.037 equals 2.404 feet. 2 feet, 0.404 times 12 to make it inches. 4.808 inches, or 848. We're going to subtract the 8 whole inches. We got the 0.848. Oops. Let's type in 0.848 here. And we're going to do times 16, gives us 13.5. So that's 14 16ths, which reduces to 7/8 of an inch. So 2'4" and 7/8. So you can see the calculation is exactly the same as with our hip roof. It's just the picture's a little different. Where we get that length here for our triangle is different. Here we had to get it because the slopes are the same, had to be half of the main roof span. That's where this next example is going to get a little more confusing. A common practice on an L roof is to make them match, make the peaks match. So let's say we've got a main roof here with a 36-foot span, an L roof here with a 24-foot span, and let's go with a 10-12 slope on the main roof. We will once again start with the common rafter. This is 36 feet, 10-12 slope. Looking for the height here. This is an 18-foot. So to find that height, we have our 10-12 slope. We got our height over 18 feet to run. We need to figure out what that height is. We're going to cross multiply and divide. Oops, somebody's mic got unmuted. If you want to double check, make sure your mic's muted, Paul. So h equals 15. That height is 15 feet high. Now, we got to find the length of that common rafter here. Obviously, as you can tell, I'm skipping some steps here. I'm doing the height of the common and the length of the common all together. That'll be the square root of 15 squared, the height squared, plus the run squared, the 18 squared. Giving us 23.431 feet. That is this length right here. Next step is we want to look at the L roof. And we're going to look at we'll call it the longest jack. It's also the common rafter on the L roof. We have this, we know two things about it. We know that the span is 24 feet, and we know the height, since the peaks match here, since those peaks are the same, we know the height is 15 feet. And of course, that means that this part is actually only 12 feet. So we're going to find this length of that longest jack, or the common rafter on the L roof, whichever way you want to look at it. As square root of 12 squared plus 15 squared, giving us 19.209 feet. That's this one here, 19.209 feet. Now we are ready to find the next longest jack in each direction. So let's do the L roof first. And we are finding that next longest jack. So on the L roof, draw this a little bit better. Of the 19.209 feet here, we need to find this dimension. Well, that dimension from our drawing is this dimension right here. That is half of the 36-foot span over there. That's 18 feet. So that means to find the next jack, I'm going to call that Y. This is Y. This is going to be 2 feet less with our 2-foot spacings. That's 16 feet. So the 18 is related to the 16. In the same way that the 19.209 is related to Y. Cross, multiply, and divide. 16 times 19.209 divided by 18. 17.075. So now we can find the decrease while we're here. 19.209 minus 17.075. Or 2.134 feet is that decrease. 2 feet. 134 times 12. 1 inch. You get that 0.608 times 16. You get 9.7, which is 10/16 or 5/8 of an inch. That is the L side decrease. So the decrease on the L side of the valley. We still need to do the main roof side. On the main roof side, we have that 23.431 feet. We need to find this dimension up here. Well, if we look back at our drawing, that dimension there is half of this span. That's going to be 12 feet. So when we put in the next rafter here, which I'm going to call X, that'll be, of course, on 10 feet there. 12 feet. Next one, 10 feet, and of course this will be X. So we have 12 relates to 10, as 23.431 relates to X. Now we can cross multiply and divide. 23.431 times 10 divided by 12 gives us 19.526. And we'll subtract those to get our decrease. 23.431 minus 19.526. 2 and 11, 5, 0, 2 and 14, so 9. And 3.905 feet is our decrease. So that's 3 feet. 905 times 12 is 10 inches. Or take that 0.86 times 16. 13.7 is 14/16, which is 7/8. So that is the main roof decrease. So the decrease on the main roof side. It's a mouthful. But you can see again the process is very, very similar to the hip roof. The difference here, of course, was, again, finding these distances for the other side of our triangle. That's all I'm going to say about the valleys. I think you can do the valleys just fine. There is a worksheet on Blackboard. I'm doing that valley jack decrease. So it's posted out there for today for that. What I'm going to do is, anybody need a short bathroom break before we go on, or are we all doing fairly well?
I think we're
Hey,
good.
let's give you 3 minutes if you need to take a bathroom break and refill your water cup or whatever, and then we'll be back at it here. Okay, it is that time. Let's go ahead and get rolling here again. Everybody a chance to get settled back in here. Okay, so for the next part of class here, we're going to talk about probably one of the things that I have found the most mistakes on in houses, and that is staircases. So let's start out with a little bit of vocabulary about stairs. So first of all, a stairway, is going to go from a lower level floor to an upper level floor. The distance from the lower level floor to the upper level floor is called the total rise. Now, it's not all done in one big step. There's two main components that go into that. There is a ceiling height in the lower level. Usually just referred to as the ceiling height because we don't care about the ceiling up above. And then there's a floor thickness. Floor thickness does include the thickness of the finished floor up above, so whether it's carpet, tile, whatever, and it includes the thickness of the ceiling down below. So it's not just your joists or your floor trusses and your subfloor. It is the full thickness of the floor. Those two items, of course, add up to make your total rise. Now let's look at the stairs itself. I'm going to put dots on the bottom there just so it doesn't look like we can actually count the number of stairs, because the number of stairs I have is really not relevant here. Each stair has a height. The term in construction that is used as a riser is often referred to as the unit rise. In other words, is the rise of a single step up, or the height of a riser. That distance there is referred to as the tread. That's the tread of the steps. Sometimes mathematically referred to as the unit run. A lot of codes involved here. First of all, tread, I believe, is a 9-inch minimum tread. I think they may have changed that in the last code update. So it used to be a 9-inch minimum tread. It might be slightly larger than that now. Typical tread is 11 inches. And usually close to that. So 10 and a half, 11, 11 and a half. Try to stay really close to that 11 inches. Unit rise, or the height of the riser, code used to limit that to 9 inches, and I think they may have cut that down. It might be less than 9 inches that you can go for that now. You can't go too tall with your risers. Typically, we stay about 7 inches for the unit rise. So the riser height stays right around 7 inches if we can. Now, of course, there's a floor on the other side over here. I'm going to interfere here with my words a little bit, but there's a height from the bottom of that floor at the edge of the opening to the step directly below it, which is commonly referred to as head clearance. I'm going to label this as simple head clearance, because code no longer allows for that to be an adequate calculation anymore. What the code now requires is called a planar head clearance. In other words, if you laid a flat, thin piece of plywood on the step so it went down at an angle like this purple line here, it's the distance perpendicular from that line to the edge of that stair opening. You can see that's considerably shorter than the red line. Most building inspectors still use simple head clearance, by the way. Anyway, the other thing we have here is stair openings. That's the distance from where the steps hit the floor on the one side to where the floor begins again on the other side of the steps. So there's two main things to calculate here. One is to find the exact unit rise. That's based on what the dimensions are that are there. So let's look at finding the exact unit rise. Let's look at a situation where we have a floor thickness of, well, let's just put it as 14.5 inches. And that lower level ceiling height at 94.5 inches. So our first step in finding that exact unit rise is to find the total rise. And that's going to be the 94.5 to 14.5. So at 95, it's 109 inches. Second step in finding the exact unit rise is to find the number of risers. And I'm going to put it as number of rises required. To do that, you take total rise, which is the 109, divided by, remember we said that unit rise is typically 7 inches. So we're going to start at 7 inches. So take our 109-inch unit rise divided by 7 inches. Of course, this will not come out exact. You get 15.5714. We're just going to say 15.57 rises. Now, if we round up, our rise will be less than 7 inches. If we round down, that'll be fewer rises, so each rise will get larger. The unit rise would be more than 7 inches. Typically, we prefer to keep it under 7 inches, so we'll make it slightly smaller. So we are going to round up on this. So that means we're going to use 16 rises. 16 is a pretty typical number of rises anyway. So now once we found the number of rises, step 3 is to find the exact unit rise. To find the exact unit rise, we take our total rise divided by the number of rises that we just calculated in step 2. So here we've got the 109-inch total rise divided by 16 rises, which will give us 6.8125. Those of you that don't recognize that as 13/16, that's 6 inches. Take off the 6, take the 0.8125 times 16, we get 13/16. That means each rise is 6 and 13/16 inches. Now in this case, that came out to exactly 13/16, which is wonderful. Makes life a lot easier when it does that. But sometimes it'll be rounded. And this is where we talked a little bit yesterday in the classroom about every second or third step, either adding a 16th or removing a 16th to do a correction for that, so that you don't get to the bottom of the stairways and that bottom step is now 7/16 taller or shorter than the others, because you won't recognize a 16th of an inch on a single step, but you will surely recognize 7/16 of an inch on one step. So that is our unit rise, 6 and 13/16. Let's do another example of that. So let's say our ceiling height let's put this one at 101 1/4 inches. A lot of times they'll go, if they're doing a block foundation, they'll do an extra block to give a little extra room for mechanicals or whatever, or when pouring the floor, they don't take too much out of the ceiling height of the basement. That's a reasonable ceiling height. And our floor thickness. We're going to use trusses here, so let's make this 22 inches. So that means our total rise is 101 1/4, 22, 123 1/4 inches. Find the number of rises. Again, we take the total rise, 123. I said 1/4 and I wrote 1/2, didn't I? And 1/4. It's 123 1/4 inches divided by the estimated rise of 7 inches each. We divide that, we get 17.607. Now again, I would rather keep our rises, our unit rise, a little under 7 rather than a little over. Depending on who you're working with, some people would rather be a few 16ths over and have fewer steps. It's just a matter of preference. So we're going to round up. By rounding up to 18 rises, we're making sure our unit rise is under 7 inches. That's one of the spots where I see people making a lot of mistakes, by the way, is they want to be under 7 inches, so they round down instead of rounding up. Your rounding is opposite of what you're going to be compared to the 7 inches. So then we find our exact unit rise, which is, once again, our total rise of 123 1/4 divided by 18 rises. 123.25 divided by 18 is 6.8472. So now off of that, we're going to keep the 6. On my calculator here, I'm going to subtract the 6 off. We got 6 whole inches. I just have the decimal left. And I do want to keep this whole decimal there. I don't want to round it any more than I have to. So I'm going to times 16 to get 16ths. That is 13.55, which rounds up to 14, which would be 7/8. 14/16 is 7/8 of an inch. So our unit rise here is going to be 6 7/8 of an inch. But you'll notice this was really 13.55. It's almost 13.5. It's really right between 13/16 and 14/16 for that unit rise. Well, on 18 rises, that half of a 16th is going to end up being 9/16 of an inch, just over half an inch. So here, what I would do, since that's 13.5, is I would use 6 7/8 and 6 13/16 inches. And I would alternate between them. So that's going to keep us as that 13.5 is right in between. So I would make the first unit rise 6 7/8, the next one 6 13/16, then 6 7/8. I would alternate between those two measurements, since the number that we rounded is really right between 13 and 14/16, to make sure that when we got to the bottom, that bottom step is really, really, really close to the same as the others. I'm within a 16th, hopefully, of the others. Have you guys try one. See if you can find the exact rise in your notes. So we have a ceiling height of 99 1/2 inches and a floor thickness again, let's go with 18. We'll keep it simple for you. Go 18.5. Hey, Scott, since you're in the room, I'm going to use your knowledge a little bit here. When you have them do stairs, cut stairways, would you rather have them go slightly over 7 inches if they have to, or slightly under 7 inches? Oh, she must be muted. Anyway, as a group, I want to have you guys in your notes find the exact unit rise for that situation. We're going to keep it slightly under 7 inches. So start off at 7, round the number of rises up so that we stay under 7 inches. I'll give you about 2 minutes, then we'll go over that. Okay, so it's been a little over 2 minutes. Let's take a look and see how you did on this. We're going to find the total rise. Be 99.5 inches. Plus 18.5 inches. 118 inches. Next, you find the number of rises, which is going to be our total rise, 118 inches, divided by that estimated rise of 7 inches each. 118 divided by 7 gives us 16.857. Again, we're going to round up so that we make sure that our unit rise is smaller. We use 17 rises. Next, we're going to find the exact unit rise. We're going to do that by taking our total rise, the 118 inches, divided by our number of rises of 17. 118 divided by 17 is 6.941. Now again, I'm going to keep this as exact as possible, so I'm going to keep the 6. On my calculator, I'm just going to subtract off the 6 so that the decimal is still there. And turn that into 16ths. We're going to do times 16 is 15.05. So that's 15 sixteenths. Now, since that was 15.05, it was really close to just 15 sixteenths. In 17 rises, that 0.05 that we rounded is going to be less than 1/16 of an inch. So we don't have to worry about doing an adjustment. If you want to look, how do we know how far that's going to be off? Well, what we would do is we would take what we rounded. In this case, that's the 0.05888 that we rounded off of that 15.08. And we could multiply by the number of rises, or 17 rises. That tells us it's going to be exactly 1/16 that will be off on the last step. We can handle being off. Code, I believe it used to allow 1/8 of an inch. I'm not sure if they've tightened it down or not. But kind of the rule of thumb, as long as you're within 1/8 of an inch from one step to the next, you're okay. So 1/16 of an inch off on either the bottom or top step, we're okay with that. Next thing I want to talk about is the stair opening. And like I said, we are going to do the simple calculation for stair opening, just going off of the top of the step below it, rather than the planer where you have to go from the nose of the steps. You have to go off that plane created by the nose of the steps. Because we are going off of the simple calculation, if you're doing the regular planer, I shouldn't say the regular, the planer stair opening head clearance requirement, the code is 6 foot 4 inches of head clearance. Well, since we're using the simple calculation, we're going to use 6 foot 8 inches of head clearance. One is because 6 foot 8 inches is the height of a door, so it's a standard number that is used a lot in construction. Also, the 6 foot 8 inches, if you look at it, the average height of one of our steps, of our riser, is about 7 inches. About 7 inches. So if we're doing our head clearance off of that, that extra 4 inches, if we're comparing that to the plane from the nose of the steps, that extra 4 inches covers us back to about a little over halfway to the next riser if that stair opening comes there. Now we will typically line up the stair opening with one of the edges of the step, so we don't have to worry too much about it. But again, that 6 foot 8 inches just keeps us from getting in trouble if we're slightly off. That's my preference. It's not something that is an industry standard or anything like that. 6 foot 4 is the code. I always go 6 foot 8 just because I've hit my head pretty hard on ceilings on stairways that were done to minimum code. So let's say we have a stairway. And we have the unit rise at tread height of 7 inches. Or sorry, riser height of 7 inches. Our tread width has to be spelled out. If it's not given, always assume 11 inches for the tread width. If it's different from 11 inches, I'll give it to you in the problem. If I don't give it to you, it's 11 inches. Those numbers are going to be important to us, as well as the floor thickness. Let's say we've got a floor thickness here. Let's go 18.5 inches. If we are assuming that our head clearance, again, has to go off the bottom of the floor to that, could have drawn that a little straighter, to the stair below it. Assuming that that is going to be 6 foot 8 inches. We need to find something called the total required drop. And this is for the head clearance. I'm just going to do HC for head clearance. So the total required drop for that head clearance is the head clearance, which is the 6 foot 8, plus the floor thickness. So here I have 6 foot 8 for the head clearance, which is going to get converted. 6 foot 8 is 80 inches. 6 times 12 is 72, plus 8 is 80 inches. Plus my 18.5 inches of floor thickness gives me a total required drop of 98.5 inches. So from the top of the floor down to that step has to be 98.5 inches. Now we need to find required number of treads. Or required number of risers to meet that total drop. To do that, it is the total drop divided by that unit rise, that riser height. So here that's going to be 98.5 divided by 7. Now this is going to come out to be just painfully close to perfect. 98.5 divided by 7 is going to give us 14.071428.571. which means 14 isn't enough. Now, because we had the extra few inches of head clearance, 14 might be enough, but to play it safe, this number here always rounds up. We always round up, which means we're going to use 15 rises is what we need to get our head clearance. Next, we need the required number of treads. In other words, the number of unit runs. Well, if you look at a step, here's a simple 4-step up from a floor to a landing. 4 rises only requires 3 treads. The number of treads is always 1 less than the number of risers. Because you have a riser on the bottom and on the top, you get a bonus one. You get one extra riser, so you only need 1 less tread. So if we need 15 risers, we need 15 minus 1, or 14 treads. So then that means our stair opening required stair opening is the number of treads, the last step, times the unit run, or the tread width. So here we need 14 treads times 11 inches each, 154 inches. We want to convert that 154 inches into feet and inches. So 154 divided by 12, 12 feet. Subtract the 12 feet, and we multiply by 12 to turn the remaining decimal back into inches. That's 10 inches. So for that situation, we need a 12-foot, 10-inch stair opening to ensure that we have the proper head clearance. We will discuss some things on Thursday about things we can do to fudge that stair opening. For right now, I think you guys have had enough. There is another worksheet in Blackboard, finding the exact unit rise and stair opening. That's also posted in today's section of Blackboard, so you can pull that worksheet down. We'll go over this stuff more on Thursday. For now, I didn't give you any work time in the first hour, so I owe you a little bit here. So I'll give you guys the last 25 minutes here to work on homework if you like. I will be on the network here if you need anything for a while. Otherwise, that is all we have for new material. So if you would prefer, you are free to go.